In this lecture, we are going to talk about synchronization issues. So we are going to introduce the topic of concurrent programming by looking at everything that can go wrong, pretty much, when you are writing concurrent code. So let's take a look at what we have as the menu for this session. So we are going to start by talking about thread synchronization mechanism. Okay, so we are going to look more specifically to two different synchronization mechanisms that are readily available in the Java language. One of them is going to operate actually at the level of the thread itself. So it's going to allow us to synchronize entire threads with one another. The other is going to be a little bit more fine-grained. It's going to allow us to operate at the level of statements. So one of the differences we're going to see between the two is that the former approach allows us to actually rely on the fact that Java offers a lock, an implicit lock inside every object. And the second one is going to allow us to define our own locks and do more fine-grained concurrency control. So to illustrate those two thread synchronization mechanisms, we are going to introduce pretty much an early version of the three problems we are going to discuss in the second part of this lecture, and that one was going to be the deadlock. After that, we're going to look at the concept of liveliness for a concurrent application. So liveliness simply means the ability of your concurrent application to make progress, okay, to still continue executing. And we are going to take a more careful look at three of the most important problems we encounter in concurrent programming, which are the deadlock. Nothing is moving anymore. The starvation, some processes are moving along, but some processes seem to be stuck, never able to acquire the resource they need. And livelock, where everything keeps moving, everybody is busy, every process is using computing power. However, we are not getting anywhere useful. So regarding reading assignments, those slides are based once again on the Oracle Java tutorial. So you should really be reading this along as you review this lecture. Other than that, we have other sources that have been used in this lecture. For example, a tutorial on Java Word. I recommend really that if you are to do any sort of concurrent programming, you take the time to actually look at the entirety of this tutorial. But more specifically, this lecture is going to be mimicking what is contained in part 2 of that tutorial on Java Thread entitled Thread Synchronization. But the whole series is a very, very useful read actually for any programmer. So let's talk about thread synchronization mechanism, and to illustrate them, to show their usefulness, we are going to put that in the context of the thread interference problem. So let me describe to you what we mean by thread interference problem. So here's a very simple class, okay, the class counter. It encapsulates a private field C initialized to 0 of type int. So the premise here is that this object of the class counter are going to be shared among multiple threads. So in the simplest scenario, we're going to instantiate one object of the class counter, and it's going to be shared by two threads, okay? Now, the methods that we provide with this class counter are very simple. The increment method is going to simply take the field C and increment it by 1. The decrement method is going to decrement the field C by 1, okay? And if we call value, value is simply a getter, an accessor on the field C. It's just going to return the value. Now, the idea is if two threads are accessing the same object of class counter, and they are trying roughly at the same time to call increment for one and decrement for the other, well, they're going to enter what we call a race condition. Okay, so a race condition means that the outcome of the increment and decrement operation are not going to be what you would expect them to be, which means increment by 1, decrement by 1, the value was not changed. Okay, one of the two process might win the so-called race condition, and if it does, then the value is going to be left in an invalid state. So all of this, you could say, well, those methods are really basic. Okay, they are really, I was going to say, atomic, but I should not use that term because it has a special meaning. But they really look like inside of each of those two methods that are potentially called by concurrent thread, we do one and single thing. So the temptation is to think, if I execute the increment method in one of my threads, it's going to increment the counter, then terminate. And there is no way that something can happen while I'm incrementing the counter, C, because it's one statement. However, even a simple statement like C++ or C++ are broken down into multiple step, multiple statement when you are looking at the bytecode level, okay? Or if you are using another language than Java that's compiled at the assembly level, for example. So when you write here C++, but this is true also for C++, okay? When you increment C like this, what looks to be a single statement is actually decomposed into 3 steps. You need to read the value that is currently stored in the field C. You need to add 1 to this value in a register, for example. And then you need to store back the result of that operation in memory inside this field. So this is why even the simplest of statements like C++, C++, actually open windows for execution between 2 threads to create mischief. So we're going to take a look exactly at how we can create some mischief here, create a race condition if we have 2 threads, one that try to increment, one that try to decrement on a shared object of class counter. All right, so we're going to trace through the code, okay? We're going to simulate parallel execution of 2 threads, thread 1 and thread 2, okay? Thread 1 is going to call the increment method, thread 2 is going to call the decrement method, and again, the key is that they call those methods on the same shared object. So let's say that the shared value here in the last column is going to be 50. We're going to keep track of which thread execute. So we are going to interleave execution, okay? So we are going to execute 1 step in thread 1, then 1 step in thread 2, then 1 step in thread 1, then again step 2, thread 2, etc. So obviously this is this interleaving of execution that causes the problem, okay? But this is something that you do not really control. The scheduler, the thread scheduler, is going to decide, when to interrupt a thread and give control to the other. So we are just illustrating here the potential problem by picking one of the order of execution that would actually cause that problem. But again, concurrency bugs are difficult to track down because maybe you are running your code right now and it features a bug because of the specific order of execution of the thread, and then you rerun it again in 5 minutes and everything seems to be operating fine because there was a different interleaving of execution here that didn't allow for the race condition for the bug actually to occur, okay? So in this table, we're going to keep track of the order of execution. We're going to label here which of the 3 steps is executed by each thread on that turn, okay? And we're going to store here the local value. I mentioned that we were going to read the value of the field into something like a register, for example, then add to that register, then store the content of the register back to the field, right? So this is what those 2 last columns represent. The rightmost column represents actually the field inside the shared object. The local value represents the register inside the thread execution context that is going to be loaded with that value, then modified, and that will be eventually returned back to the shared object here. So let's step through this program. So we are going to start by assuming that thread 1 gets executed first, okay? And we saw that in order to increment C, in order to execute the statement here C++, it needs to first read the value inside the shared field C into a local register. So this is what happens here on that second row of the table here. The shared value on the first row was 50. Now 50 has been copied into the register for thread 1. Then we switch to thread 2. Well, thread 2 is trying to call the decrement method. It's trying to execute right now the C statement. So the first step again is to read the value from the shared field. And up to now, we don't have any problem, right? The shared value has never been modified, it's 50. So whichever order thread 1 and thread 2 read that value and copy it into their local register doesn't really matter, Okay, so far we have parallel execution that is not causing problem. Then we switch back to thread number 1. When we switch back to thread number 1, now thread number 1 is going to execute the add part of its operation. So it takes whatever it read from the shared field, for value 50, it adds 1 to it and stores the result inside its local register. So we have 51 here inside the local register. And we switch back again to thread number 2. Thread number 2 is at roughly the same, in the same step of the process, except that instead of adding, it wants to subtract. So it's going to take whatever it read from the shared field, which was 50, and it's going to decrement it by 1. So we get 49 in the local register for thread 2. So we have values here, 50, 50, 51, 49, okay? But keep in mind that when I'm talking about thread 1 has its own version of the shared value copied into its own register. So this register that contains 51 is in thread 1, this register that contains 49 is in thread 2, okay? So we have 2 copies of the original shared value, and now you can see that those 2 copies have diverged, okay? They are differing now. And then the last step is for both of those threads to actually copy back the result of their computation into the shared field. So we move back to thread 1. Thread 1 is going to execute a store operation that's going to take whatever it has in its own local register, which is value 51, and copy it, overwrite with it the shared field value. So we had 50 in the shared field, now we have 51, because 51 was in that register, computed here, and appearing here as well. And then we move to thread 2, and this is where you see the problem. Thread 2 is also at the same level of progression in its operation, so it's ready to store the result. It's going to apply a store operation to its own local register, which contains 49, okay, 50 minus 1. And it's going to store that value into the shared field. So now we went from, we had 50 originally. When thread 1 completed its job, which was adding 1, we have 51, which makes sense. But when thread 2 completed its job subtracting 1, we have now 49 that is overwriting 51. So the result we expected was if you add 1 and you remove 1 in parallel, well, you should still have the initial value, 50. You can see here that there was actually a race between the 2 threads to get priority in overwriting the shared value with their own computation result. And in this case, thread 2 won the race. Okay, clearly won the race, because even though thread 1 did its job, wrote back the result, and that result was correct, that result was lost. And it's thread 2 that wrote its own result. Unfortunately, thread 2 has based its calculation not on the result produced by thread 1, which was 51, but on the original value. So this is where we have this problem emerging here. So we have interference between the 2 threads. We have a race condition. There's a lot of terminology here to introduce, but the bottom line is that you can see the kind of problem that can happen even with very simple, simplistic even code, like the code that we have here on the left side of the slide. So now what can we do about that? Okay, so we got a taste of one of the different kind of problems that can happen in the context of concurrent programming. Now we're going to look at one of the solutions that the Java programming language provides us with. So the first solution we're going to talk about, synchronizing entire method. So let's take a look at the code that we had so far. We had a counter class, okay? We are going to slightly modify it. So now we are writing the class synchronize counter. We still have this private field that's meant to be shared, okay? And then our 3 methods that we had before, the increment, decrement, and value method, we are going to mark them with the keyword, the Java keyword, synchronized. And that's all we have to do. So very simple, okay? That's one of the reasons behind the original success of Java. Java is one of the first mainstream programming language that actually provided out-of-the-box high-level and very practical tools to actually engage in concurrent programming. So you can see here that trying to lock actually our code so that it doesn't feature this concurrent programming bug is relatively easy, okay? And we, by the way, we did a little bit of overkill here by putting synchronize everywhere, but we're going to talk about it again in a few minutes. So before we go any further, let's talk a little bit about what synchronized and the synchronized keyword do in this example. So at the level of our class, okay, when we have an object of that class synchronized counter, the fact that we marked some method as synchronized means that if we share that object between several threads, only one of those threads at a time can call one of our synchronized methods. Okay, so you could, if we had methods in that class that were not marked synchronized, every thread, every number of threads in parallel could call those methods without any issue. Okay, but if one of them calls one of our synchronized methods, then suddenly another thread trying to call another of the synchronized method on the same object will be put in a wait queue. It's going to have to wait for the first method that called any of the synchronized, it's going to have to wait for the first thread that called any of the synchronized method to complete that method, to terminate that method, before to be allowed to enter another synchronized method. Okay, so that's the main thing. So in our case, what we did is we have some read and write operation. Okay, like the value method is really an accessor, so it just returns a value. We could have done without marking that one as synchronized. Okay. Reason is that if you have a shared object that contains the value 50 and you have a million threads that are trying to read in parallel the value 50, there is no reason to make them take turn. Okay, the issue that we previously described, thread interference, only happens when threads are trying to read and write values that are shared. Okay, if you are just reading, there's no need for synchronizing. Okay, so we did a little bit of overkill here, but the idea was, well, let's try to synchronize all of our read and write operation on whatever we are sharing, that field. And then this way we are going to avoid completely, for sure, any memory consistency issue due to the thread interference problem. Okay, that was the idea to start naively solving those problems. So I mentioned that if we are just reading, we could have done without synchronizing. Well, another thing that's worth mentioning is that if your shared field is a final field, so that means that as soon as it's assigned a value, that value will never be changed afterward. But then again, you are in a scenario where you cannot mess up, right? You are going to end up treating that field as read-only. So again, it's like if all of your methods, were just there to actually read from the field. So generally, if you have final fields that are shared, you're not going to have to worry much about synchronization either. Regarding the implementation under the hood, I already mentioned that, but let me reiterate it here. When you say that your threads are synchronized in a class, I told you that means that only one of the multiple threads, sharing an object of that class is going to be able to enter into one of the synchronized methods of that class at a time. Well, this is actually made possible by the existence in the Java implementation of a lock inside each object that you create. So each object you create has what we call an intrinsic lock associated to it by the Java virtual machine. You don't have to declare it, you don't have to manage it. However, when you say, I want to synchronize one or several methods, that means that some code is generated automatically on your behalf so that when you enter the method, well, that thread executing that method code is going to try to acquire that lock. If the lock is already acquired by another thread that entered another of the synchronized method on that object, then too bad. You are going to have to wait. So your thread is going to be frozen, waiting for the lock to become available. If you are the first one to call a synchronized method on that object, you take the lock, thus preventing any further threads to call any other synchronized method on that same object. You do your job, you execute the code of the method, and then when you're done, automatically Java on your behalf, when you exit the synchronize method is going to release that intrinsic lock associated with the object. So that makes it really easy to synchronize access, to data that has to be shared among threads, as long as you encapsulate it into an object, a Java object. Just as a side remark, what is true for objects in Java, the fact that they each have an intrinsic lock, is also true for classes. So if you are talking about, well, even without going into meta programming, okay, if you are simply talking about having static fields in a class, and you want several concurrent threads to access those static fields in a class, well, you can have static methods that are marked synchronized to allow to control, the possibility to mitigate the possibility for thread interference. Okay, so the same way that we can mitigate thread interference at the level of instance variable fields inside the object of a class, we can also mitigate thread interference at the level of class variables, okay, static variables in classes. So let's talk now about the second approach to try to mitigate, these problems that we describe here. So we're going to talk about synchronized statements. So the idea is the same, and actually the syntax is going to also use the keywords, the Java keyword synchronized, okay? So the idea is the same, but this time we have more degrees of freedom. When we synchronize a method in a class or a static method in a class, they use the intrinsic lock for the object of the class. We don't have a choice. Now we are going to be able to specify when we want to synchronize a block, what kind of object we want to use to lock things. So what kind of lock do we want to use, pretty much? Let's take a look at this. So we have here a public class something. It's going to be twice pretty much what we did with the counter, insofar that we have two data fields here instead of just one, okay? And we're going to assume that those two data fields, data1 and data2, are completely unrelated. Now we have a get data1 and a get data2, so we have accessors on each of the fields, and we mark those as synchronized. Again, first warning, all right, the question is, what are your thoughts on this design? Well, that's a bit of overkill here, because if those are really only accessors, they don't modify the value of data1, data2, we do not have to mark them synchronized. But then we have the setters, set data1, set data2, and those are going to update, based on a parameter they are given, the values of each of the shared field. Well, we've seen already in our previous example that these mutators, these setters, have potential for thread interference, so these guys need to be synchronized. However, the thing that is a little bothering with this example is that we mentioned here that we have two unrelated fields. So that means that when I try to set data1, if in parallel another thread wanted to set data2, theoretically I should allow it to do it, because the fields are supposed to be unrelated, so I'm not going to use data1 to modify data2 or something like that. Unfortunately, because of the synchronized mechanism, I cannot do that. More specifically, remember I said we have one lock per object. So if that class was really focused, okay, and objects of that class were only, wrapping around one of the two data fields, that would be fine. This is an example we saw previously with our counter. However, as soon as you have a class that has multiple data fields, and that's going to happen, and those data fields are relatively independent, then by using synchronize and the single lock for all the objects, you force every method that wants to do anything with any of the fields in your object to wait for that other method to be done processing that one field. And that's really inefficient, okay? So this is a case where we have overlooking, all right? We exclude any sort of operation, even though we know that our two data fields are somewhat independent, and we could do a lot better than this. All right. So we're going to look at solutions here to try to make the code a little bit more flexible. Obviously, the solution is the topic of this section of the lecture, which is synchronized statements. So what are synchronized statements? Let's take a look here at the code example we have on this slide. Okay, we have a public void method named add name, takes a parameter string name. Okay, so it's just a method that's going to modify the state of an object. Okay, we don't care really about the class, we don't care about the object. We just want to illustrate that this method here is not marked synchronized. However, inside the method, the part where we are going to say, for example, I'm going to modify my object field last name based on the value of the parameter, then I'm going to modify another field named name count and increment it and stuff like that, then add the name to a list. Well, that part here where I modify the shared field last name and name count, I want it to be synchronized, but only that part. Okay, so how do I do this? Synchronize keyword like before, except that here it's not used to prefix, a method. I'm going to specify to synchronize between parentheses where is the object, which intrinsic lock I want to use to achieve synchronization. So in this case, I pass my implicit parameter des to synchronize, which means that I'm going to pretty much use my intrinsic lock for this object on which a method is called to do the synchronization. So in this case, it's not really much better than having a synchronized method. But we're going to see other example where we're going to use more flexible settings, okay? But the idea is, let's introduce the syntax first. So instead of saying I'm going to always use the intrinsic lock for this object, I have to specify as parameter, here's the object in which I'm going to find an intrinsic lock, and that's the intrinsic lock I'm going to use. Okay? So, looking at this code, the question obviously is, well, does this solve our problem? Not really. Okay, not really, and again, I mentioned it, we're using this. So that means that we're looking at the object on which a method is being applied. This object, we're looking at its intrinsic lock, okay? And so this is exactly the same thing that if we had synchronized the whole method. All right, so let's try to do a little better than this. Let's take a look at another class, okay? This class has two different fields that are going to be shared. So two counters, let's say, initialized at 0. And now we are going to define two objects, which reference we're going to put in two private fields, log1 and log2, okay? So we create two objects. So generally, there's not much benefit into creating an instance of the class object, okay? But here, we really do not need to create an instance of any specific class, okay? We just want really the most basic object that Java has to offer to us. Why? Because every object, even the most basic object of the class object, uppercase O, features an intrinsic lock. And what we're doing with the synchronize keyword here is we are just passing an object reference as parameter to synchronize, just as a way to say, hey, here's an object, use the intrinsic lock inside that object to do synchronization. So we really don't need those objects to do anything if they are just going to be used as locks, okay? So we create two objects. One, log1, is meant to synchronize access to the field C1. Log2, similarly, is meant to synchronize access to field C2. And here are two different methods in this class, public void increment1, public void increment2. As the name implies, they are actually mutators. The first one is going to be meant to increment the field C1, the second to increment the field C2. So what we do is, instead of marking inc1 and inc2 as synchronized, which means that while I increment C1, I will not be able to increment C2, even though those are two operations that might very well apply in parallel without any problem. So now I'm using this new synchronized statement syntax. So what I say inside the method inc1 and inc2, I say I define a synchronized block of code. So synchronize log1, and the block of code is C1++. So for me to be able to increment C1 inside the inc1 method, I need to first acquire the intrinsic lock of the object referred to by the field log1. So if two parallel threads try to call inc1, one of them is going to be blocked waiting for the first one to finish before to be allowed to increment again C1. Okay? But if I have two threads executing in parallel and each one of them calls respectively inc1 and inc2, then the first thread calling inc1 is going to take the lock1 increment C1. The second thread in parallel, without having to wait, is going to take the lock number 2 and increment C2. And then when they are done, they both release their lock. Okay? So that brings flexibility. That means no, I do not have to use always the one intrinsic lock provided in the shared object where I call of my method. Even though I have one single shared object between a multitude of threads, okay, I can actually have different locks inside that object now, and I can use those locks to do a finer grained, synchronization between all of the parallel threads. All right, so that's good. Now, the problem is we are handling our lock quite explicitly. Okay, so in the past we have always tried when we had those extra steps, creating a lock, dedicating a lock to a certain field, etc. We tried to simplify. So let's try to simplify and see if that would work. Okay. If it works, then good. We have a better programming practice that we just learned. If it doesn't work, then we know the limit of how much we can simplify. So what we want to do here, and that is illustrated by those 3 lines of code, is every time we define a synchronized block, instead of having to manage, lock 1 and lock 2, etc., we're just going to say, I need a new lock. So we create an object on the fly, and we pass a reference to that object to synchronize. So it's going to use the intrinsic lock of that object. So think a little bit about this solution, pause the video if you want, okay, and try to figure out why it's not a great idea. The problem with this approach is that if we have 5 different threads running in parallel, and each of them are, let's say, calling the same method, dealing with the same field, okay, so we would expect to have one lock protecting that one field, okay? Well, in this case, because we create objects on the fly, then every thread that is trying to enter that method is going to have its own object created on the fly. Once it has its own object, well, it has inside that one object its own intrinsic lock that has been created just for its execution. So every thread is going to actually try to acquire an intrinsic lock, okay, and each thread is going to get it, no matter how many threads are trying to do the same thing in parallel, simply because each of them has its own lock created on the fly. So there is absolutely no synchronization going on there. So be careful about, it's always a good thing to try to simplify, a solution refactor. Just be careful about not oversimplifying like in this example. So we're going to talk now about the concept of liveliness, which I'm going to define real quick right now, okay? Liveliness is the concurrent application ability to execute in a timely manner. Pretty much you have multiple threads executing concurrently, and we want to make sure that each thread is still making progress toward its goals, okay? You're not stuck. So the first example of problem with liveliness of a concurrent application is going to be the deadlock that we already discussed. So let's again take a look at an example of deadlock. Okay, we already covered that, but let's just refresh our memories real quick. So we have 2 threads. We have 2 threads and we have 2 locks on a shared object. So we are going to assume that thread 1, T1, acquires lock 1. Then T2 acquires lock 2. And this is a setup for the deadlock, okay? Each of the threads has acquired one of the 2 available locks. And they are going to hold those locks, because they need to lock, the resource associated to lock 1, and to lock also the resource associated to lock 2 to do their job. They need both resources. However, they acquire the locks for each of the 2 resources in a different order, right? So T1 has pretty much half of the locks it needs, T2 has half of the locks it needs, and now comes the time for quote-unquote negotiation. T1 is trying to acquire lock number 2, but lock number 2 is already has already been acquired by T2. So T1 is blocked, and it's going to be frozen, waiting for lock 2 to be released by T1. Okay? Lock 2 to be released by T2. Now, meanwhile, the next thing that's going to happen is T2 is going to try to get the second lock it needs, which is lock 1. However, lock 1 is already held by T1, and T1 just went frozen, waiting for lock 2. So now T2 is going at its turn also to become frozen, to block, waiting for lock 1 to be released. But it's still holding lock 2. So each of those two threads finds itself in a situation where it has one of the two locks it needs. Okay? And it's waiting on the overlock, but that overlock is held by the other thread, which is also waiting for the first lock to be made available again. So that's not going to go anywhere. Okay? Your application is going to freeze. Your two threads are going to stop making progress. They're going to remain frozen forever. So that's the idea of the deadlock. Let's illustrate it with an example that is a little bit more concrete. Okay? So it's usual to use bank accounts and stuff like that to illustrate concurrency problems. So let's go. We have a class bank account, inside of which we have a field balance and a field ID that allows us to identify the bank account. So the constructor is very simple. Okay, pass an ID, pass a value for balance, assign the ID to the field ID, assign the balance parameter to the balance field. Okay, so nothing really complicated there. Then we have a withdraw method that we are going to detail in a second, so I didn't put the code here on the slide. The deposit method, same thing, we're going to detail it on its own slide, so there's no code here right now. And then a transfer method, again, that's going to use withdraw and deposit. Okay, so we are going to specify as parameter of a transfer which bank account we're transferring money from, which bank account we're transferring money to. So it's a static method. Okay, it doesn't operate on this instance of bank account here. We're going to give two reference to bank accounts, and then we specify how much we want to move. And pretty much, again, I don't give the code here because it's going to be detailed in the upcoming slides, but you can guess already that we are going to try to withdraw that amount from the from bank account, then deposit it in the to. So it's kind of like a transaction. Okay, this method encapsulates a transfer of money transaction. And then we have a public static void main method that we are going to cover last. Okay, and again, no code here. I'm going to cover that in the upcoming slides. So let's talk about the withdraw method first. So it doesn't return anything. It takes an amount. So you call it on a specific object. It's going to try to withdraw that amount from the field balance inside that object. So what we do inside the withdraw method is we simulate a lengthy, a time-consuming operation. Okay, so here our operation is simple. We just subtract amount from balance, from the field balance. So that takes almost no time. So to make it more realistic, to make it look like we are actually doing something, accessing a database, etc., and to open more potential for race condition, we are going to simulate work here by sleeping. Okay, by putting the thread in sleep mode for a certain amount of time. Okay, so that's the withdraw method. Now let's take a look at the next one. Deposit method. Again, same kind of modus operandi, okay? Returns nothing, takes an amount. We simulate that it takes a little bit of time actually to deposit that amount on the balance of the object on which we are called, and then we simply increment the field balance by the amount that was specified. So we have deposit, we have withdraw. Now we're going to use them to implement transfer. So transfer, again, is a static method. So it's not going to apply to the object on which we call it. We just call the transfer method on the class bank account, okay? And we specify as parameters the bank account objects that we want to be part of the transfer. So the method itself returns nothing. It takes a bank account reference from, a bank account reference to, and an amount. And now we have a synchronized block, as we just learned to do in the previous parts of this lecture. That synchronized block is trying to acquire the lock associated to the bank account object specified by reference from. And once it gets this lock, then it's going to use the from object to withdraw a certain amount. Once it has done that, it's going to now synchronize, use a synchronized block with a to object as an intersync lock. So we're trying to get the lock on the bank account object to which we want to make a deposit. When we get that lock, we use to.deposit to deposit the same amount. So we take the amount from, we deposit it in the object referenced to by to. So you see the pattern here, okay? We have two locks, okay? We have two resources, two bank accounts. Each bank account has its own intrinsic lock. So I first get the lock on from, and I keep the lock that I get on from, while I withdraw money from and then attempt to get the lock on to. So to go back to our previous example, this is where there's going to be potential for mischief, okay? Once you are holding that from lock, if another thread is trying to do the inverse transfer from the account referred to by to the account referred to by from, well, this is when we can have each thread, acquire one of the two locks and never let it go, thus causing the other thread to be also stuck. But we're going to get there in a minute. For now, let's look at the main method. That's the last method we need to define, okay? So we are defining a bank account identified by number 1 with $100 in it, and a second bank account identified by number 2 with $100. We store the reference to the first bank account in a variable foo account, and the reference to the second in a variable bar account. Then what we do here, okay, so watch out for the syntax here. We're doing things on the fly. We're doing twice the same kind of work, okay? So we say that we want to create a new object. We want to create a new object of the class thread. That's what it looks like here, except that we open a curly brace. So that means that we are going to define here on the fly an anonymous class that inherits from thread, implements the interface thread more accurately, okay? So inside this class, the only code that we're going to add is a public void run method. So the thread class actually implements the interface runnable, okay? That runnable interface only requires you to provide the code for a run method. So that's what we are doing. So good typical use of anonymous classes, okay? In that run method, we are going to say that we call the transfer static method from the bank account class, and we say, I want to transfer $10 from the foo account to the bar account. Okay, so I use those accounts I defined here sooner in the main. And then I close my curly brace here for the definition of the method, close the curly brace for the definition of my anonymous class, that's extending thread, sorry. And then on the fly, as this object of that new class is created, I call the start method on it. Okay, so very terse notation. We chain everything here without having to assign, temporary instances to variables and stuff like that. Same thing here. We create a new object. This object is of a class that actually extends thread, an anonymous class that extends thread. The only thing I define in my anonymous class is again the run method, and the only difference with the previous one that I did just above is that now I want to transfer $10 from the bar account to the foo account. So the opposite of this transaction here. And then I start this thread immediately as well. So let's take a look at what's going to happen when we run this code. Okay. So first thing that's going to happen here, thread 1 is going to start. Okay, so this is the one that wants to transfer $10 in one direction. Then thread 2 is going to start, the one that wants to transfer $10 in the other direction between the two accounts. Thread 1 is going to try to lock the account foo. Since nobody is actually locking the account foo, the lock is not a problem. It's acquired immediately by thread 1. Then thread 2 is going to try to lock the second account, the account bar. Okay. Again, nobody is locking that account so far. So the lock is granted. So thread 1 is trying to go from foo to bar, and thread 2 from bar to foo. The first step for each of them is to acquire the lock of their source account. And since they are using two different accounts, there's no problem. There are no problem. This happens in parallel without any sort of contention. And then thread 1 tries to lock the account bar. Well, yes, because it wants to transfer money, remember, from foo to bar. So it has a lock on foo. Now it's ready to get the lock on bar and actually deposit the money that it just withdrew from foo. However, thread 2 is already holding the lock on the bar account. So thread 1 is unable to get its second lock. So it's frozen. It goes to sleep, waiting for that lock to become available. Same thing is going to happen to thread 2, but other way around. Thread 2 is going to try to get the lock on account foo. It already has the lock on account bar, okay? But thread 1 is already holding that lock on the foo account. So thread 2 goes to sleep, is blocked, and it's going to wait for that lock to become available, and this is never going to happen, okay? Both threads are waiting for each other to release the second part, the second resource that they need to complete their transaction. So it's exactly the same scenario that we saw in the initial slide, where we are looking at it in a way a little bit more abstract maybe, but you see it illustrated here with actual code that you can test, that you can run, and that has a more pragmatic purpose. So still talking about liveliness, we are going to talk about a second category of problem that impedes the liveliness of a parallel application. So we are going to take an example of a phenomenon known as starvation. So let's try to first define it, a little bit abstractly, and then we're going to look at a real life example of what starvation can be. So we have a thread T1, and this thread is unable to get regular access to shared resources with other threads, and is unable to make progress due to the shared resource being made unavailable for long period, because they are locked by other greedy threads, quote unquote, that keep pretty much on reacquiring the lock on those shared resources. So that's a first definition of starvation. An example, not too concrete, but abstract. An example would be, we have an object O1 that has one synchronized method, and this synchronized method takes a long time to return, to complete, okay? We have a thread T1 that invokes this method repetitively, all the time. It keeps calling that method. So if that happens, T1 is going to actually lock the object O1 for long period of times, because every time it calls that synchronized method, O1 is going to be locked for a long period of time. And then as soon as it's done, well, chances are that it's going to try to call again. So there are long period of time during which no other thread can call that synchronized method or any other synchronized method on O1, okay? And then there is this tiny little window of time between the moment where T1 returns from that synchronized method and between the moment where it calls it, like almost immediately. During that tiny window of time, an other thread has a chance to call any other synchronized method on object O1. But this is a tiny window of time compared to the length of the duration of that one synchronized method that T1 keeps calling, okay? So if you want to take a real-world example of starvation, and kind of a humorous one, let's say we have an older gentleman here that is trying to hail a taxi, but we have a bunch of people waiting actually for the taxi. And every time a taxi stops a few feet away, there's a younger fellow that just rushed to the taxi. And this gentleman here keeps actually asking for more taxi to stop, but there is such a small windows of opportunity, between the time he just waited 5 minutes for a taxi and the time where one of those young, eager people is going to jump on the taxi ahead of him, that is never going to catch a ride, okay? So it's kind of, it's the same idea, that the race condition. It's the same idea also that you find well, it's not exactly the same idea that you find in deadlock. It's actually quite different. It's more of a matter of, you don't have enough opportunities to actually get a lock, Okay, you keep waiting and waiting for this long process, and then you have like maybe a few microseconds to actually take the lock, and you contend with a bunch of other threads. So it's your probability of making progress that is reduced. Okay, it's not completely grinding to a halt like with the deadlock. Okay, it's just that you have very hindered progress. Okay, so that's why it's called starvation. You are starving for resources. You are starving for access to that resource which lock is completely monopolized by another thread. So let's do what we did with the previous concept. Okay, let's take a very concrete example that you can actually run in Java. So we are going to continue with the theme of those bank accounts, okay? But now we are trying to implement a new thread. So we are going to have like different thread for a different operation running between bank accounts, different transfers. But on top of that, we are going to have this thread here implemented by objects of the class balance monitor. And that thread is going to wrap around an account. So you can see that one of the private fields of the thread is a bank account reference named account. And when you use the constructor, you specify which account you want your object of class balance monitor to wrap around, okay? And that object is going to be executed in a thread, and all it's going to do is check the status of, check the balance of that bank account. So let's take a look at how it's going to do that. So we, in our class balance monitor, we implement the runnable interface. So we are going to have to provide a run method that's going to allow us to execute that run method into a thread, okay? So that run method is going to just say, okay, here's my my ID as a thread, and I just started execution. And then we have a while true loop, and this while true loop is going to keep ad eternum checking the balance on the account that was specified in the constructor. And we keep checking the balance, so we call the getBalance method. It takes a little bit of time, okay? And then if we get a result that is negative, then we do something, we raise an alert, we send an email, a SMS, make some clouds of smoke to notify the owner of that account that the balance is negative, and we break out of the loop, thus displaying on the screen, I did my job, okay, hey, this is thread, again, the idea of the thread here. I did my job, the account I was monitoring just became negative, so I sent my warning and I'm done, okay? To put all of that in context, we are going to still need, bank account classes and stuff like that, so let's take a look at that part of the code. We are going to have a class transaction, which is really implementing the idea of the transfer static method we used previously. It also implements runnable. So we're going to be able to take objects of that class and run them in their own threads. We have three fields, two bank accounts, the source and the destination of the transfer, and an amount that represents how much we want to transfer. The constructor is going to take all of those things as parameters, so a source account, destination account, and an amount, and assign them to the corresponding field. So nothing very difficult there. And then because we implement runnable in that class transaction, we're going to have to define a run method. So here it comes. The run method is going to say, okay, here's the ID for my thread, I'm starting execution. And then when we are done, it's going to display a similar message saying I completed execution. And in between, it's going to call a transfer method onto the source account. So it's a different transfer method. It's not a static transfer method like in the previous code example we used. This one is an instance method. So the source account is going to be asked to transfer to a specified destination account the specified amount. And that's it. Okay? So let's take a look at the bank account class. Bank account class that we are going to use in this example has a balance, an ID. So the same thing than previous examples so far, okay? You see the constructor is just setting the fields to whatever values were specified in the parameters, sorry. And then we have a synchronized method, getBalance. So the catch here, no pun intended because we are using a try-catch statement here, but the catch here is that we again simulate that we have to do some lengthy work, access a database, whatnot, okay? So we open the door for like this getBalance operation to be significantly longer than what it would be if we just return balance, okay? And this is a key for the starvation. The key is that calling this method is not instantaneous. It's going to take a while. And you can see that we have like an order of magnitude 10 times the time we simulated with the previous example here. So it's supposed to be a long method. And then we just return the balance when we are done waiting, okay? Other method we are going to have defined on the bank account: withdraw, deposit. They act exactly as they did in the previous example. They are synchronized. And then the transfer method, which is now in this code example an instance method, it is synchronized as well. So we call it on an object that is pretty much the source bank account, and we pass the destination bank account as parameter. So all we do is withdraw from ourselves an amount and deposit it in the target destination bank account. And then we need a main method, so we are going to define it in the next slide. So this is the main method for this class bank account. Here it goes. So we need a bank account that we're going to refer to with variable 1 and a bank account with variable 2, so they are identified separately. They each have $500 on their balance. And then we are going to create a balance monitor. Okay, so we create a new object of class balance monitor. We ask it to monitor account 1, and we give it the name balance monitor. Then we pass this object immediately because this object is of a class that implements runnable. It can be passed directly to a Fred class constructor, and we create here a new instance of a Fred object that's going to be able to run the run method of that balance monitor object. And we do the same here for the transaction. So we are illustrating different ways to create objects on the fly and run one of their methods, inside its own thread. Okay. So thread T1 is going to run a transaction from account 1 to account 2 for $250, and thread T2 is going to run in parallel a transaction between account 1 to account 2 for $250. Okay, so here we don't have reversed account 1 and 2 destination source. Okay, we're just trying to make several transactions happen in parallel. But here's a catch. I mean, one of the catches. Okay, we say that our thread balance monitor is going to get the highest available priority. So not only this balance monitor is using that get method that takes time to execute, but it's going to get a higher priority of execution, which means it's going to be scheduled more often. So because of its nature, the balance monitor thread is going to keep calling get balance on the account that it's monitoring. So every time it successfully calls get balance, that account is going to be locked out for any other synchronized method call. Okay, it's going to take a while to get the answer, and then as soon as we get the answer, small tiny window of opportunity, and we call again get balance. And not only that, but we made sure that this thread is going to execute more often than T1 and T2. So we are just making it the perfect setup for starvation to occur. T1, just again to compound on all of this, we set the priority of T1 and T2 to be the lowest possible priority. So not only we boost the priority of execution of the balance monitor thread, but we reduce to the smallest possible value the priority of execution for threads T1, T2. We start the balance monitor thread at this point after having configured the priority, and then later we actually start T1 and T2. So we wait a little bit, we'll give a head start to the balance monitor, then we start the two threads that are just trying to make a transaction between account 1 and account 2. So all of this slide is really critical in showing you to what length we went to make sure that starvation would occur. Okay, again, starvation is one of those concurrent programming bugs that can be very transient. You can see starvation occurring, you rerun your program, everything seems to be all right. Okay, so here, this example really tries to stack the odds in favor of starvation occurring, just to demonstrate it. And then let's take a look at what happens when we finally run this code. So the balance monitor locks account 1. That's the account that it's supposed to monitor. That's the only account it's going to lock, okay? T1 tries to acquire the lock on account 1 because it's trying to, remember, move some money from account 1 to 2. It cannot because the balance monitor is holding the lock, so it waits, okay? The balance monitor reads the balance value, finally gets the result of the balance on account 1. Now it unlocks account 1. So a lot of time elapsed, okay? Like we had something like 1,000 seconds in our sleep for that get balance method. But then immediately it reacquires the lock on account 1. T1 retry to acquire the lock, okay? Cannot. Balance monitor still holds it. Balance monitor gets into another of its cycle, reads the balance, unlocks the account, but then there's not enough time for T1 to get actually the lock. And there we go. We go again, we go again, we go again. And we haven't even like put T2 on the picture here, but T2 is going to try to do exactly the same thing as T1, okay? So the chance is that T1 and T2 get their lock in that small window of time where it's available, very, very negligible. And the more threads like T1, T2 you have, the more of those threads are going to suffer starvation, even if one of them occasionally is capable to take the lock. The last problem we are going to talk about in the context of liveliness is going to be the problem of a live lock. So there is a very simple and everyday life kind of way to illustrate live lock. Live lock means that everybody is working hard, but we are going nowhere. Okay, so let's say that two people are passing each other in a narrow hallway. Okay, they are both, let's say one of them is walking on the left side of the hallway. The second person is walking on her right side of the hallway. So they are facing each other. So they bump into each other, they are face to face, and they want to try to avoid each other. So one of them is going to step to their left, the other is going to step to their right, and there we go, they are again facing each other. Okay, so what they do is they move again. So one of them step to their respective right, the other to their respective left, and they are facing each other again. And it goes on like that for a little while. So the key is that both agents in that scenario are active. Okay, if they were threads, they would be executing code. If they are, like in our example, human beings in a hallway, they keep moving, they keep burning calories, trying to move right and left, trying to find a way out, okay? So there is work being done, but there is no progress made. The situation is just like with a deadlock, okay? The situation is stuck, but we are still actually somehow managing to execute code even though we don't make any progress. So again, as usual, let's look at another concrete example, another example of code that you can run in Java that will illustrate this. So we are going to use another part of the Java util concurrent library. We are going to use reentrant locks, okay, just to enable this kind of live lock situation. So we have a live lock bank account class. Again, balance ID, nothing new. A constructor that takes balance ID as parameter, assign them to the field, nothing new. And then we have a field in that class, lock, and we create a new reentrant lock that we assign to that field. So it's kind of like what we did when we had synchronized blocks and we used two objects as locks, except that here we are using an object of class reentrant lock that offers more features that we are going to illustrate in this example. So we can do more things with those kind of locks than just try to synchronize on them. So let's take a look at the two core methods of all of those bank account class that we have been talking about until now, okay? The withdraw and deposit. So let's start with withdraw. We are going to withdraw an amount, and this time we return a Boolean value that's going to tell us if the withdrawal went through or not. So how do we do this? So we access the lock field that we just defined, and we call a method on it, a method from the reentrant lock class that is named tryLock. The beauty of this method is that it's going to return to us a Boolean. It's either you are capable to get the lock, in which case the Boolean return is going to be true, and that means that you have the lock, you can proceed. Or if you cannot get the lock, instead of blocking the thread so that you are like stuck and waiting for the lock to be available, it's going to return false, which in this case would allow us to determine, okay, we were not able to withdraw, to execute this code here that withdraws the amount specified as parameter. So we're just going to return false so that the caller of the withdraw method knows that we were not able to go through with our operation. So that allows you to make more efficient concurrent code, okay? That allows you to test a lock, and if it's not available, instead of not doing anything until the lock becomes available, you can move on and try to do something else. So that's the key of retaining some liveliness in your application, obviously. But then again, this is also what's going to enable us to get stuck, where we keep trying to do something else and we come back to that same problem and there's no progress made. But anyway, let's assume that we got the lock, okay? So if we try the lock and the lock is available, the try lock method returns true, which allows us to trigger this code here. So again, we sleep a little bit to simulate an intensive operation. Then we decrement our balance by the amount that was specified as parameter. And we return true to say, okay, I was able to perform my withdrawal operation. Now, we have taken care of the withdrawal method. Let's take a look at the deposit method. Deposit method is going to be very, very similar. As a matter of fact, the only thing that changes is minus here became a plus. Okay, but the logic is the same. Try to get the lock. If I get it, simulate some work. Okay, increase the balance by the specified amount, then return true. Otherwise, return false. Now that we have deposit and withdraw, we can again implement the transfer method. Okay, so we are going to call it try transfer in this case because again we are relying on that try lock method from reentrant lock class. So try transfer returns a boolean again telling you if the transfer went through or not. It takes as parameter a livelock bank account reference, which is a destination account. So it works like the transfer instance method in the previous code example, but not the transfer static method in the first one that we covered in this lecture, okay? So you call try transfer on an object of class livelock bank account, okay? This is going to be the source bank account. You pass the destination bank account reference as parameter and the amount as second parameter. So, and now we look at those withdraw and deposit method, and we use the fact that they return to us a boolean to let us know if that went through or not. So first we try to withdraw the amount from the livelock bank account on which the try transfer method was called. So we call des.withdraw amount. If withdraw returns false, which means I was not able to withdraw money, then I return false. I'm not able to do the transfer. If it returns true, then I try to acquire the second lock I need, okay? And I do that by calling deposit on the destination account with the amount value. And deposit is going to try to acquire the lock. If deposit is able to actually acquire the lock on that destination account, then I was able to make the withdrawal and the deposit, I return true. The transfer was successful. If not, then what I have to do is I was not able to deposit the money I withdrew from my own account to the destination account. Fine. I'm going to try again later. But in the meantime, I need to redeposit my money that I just took away from my livelock bank account on that same livelock bank account. So I undo this des.withdraw operation here on top by doing a des.deposit of the same amount. Okay? So it's really an undo statement pretty much. Let's take a look at the main method. So I need two bank accounts. So these are going to be livelock bank account in this code example. The foo account and the bar account, each of them are identified by a different number. Each of them has $500 on it to start off with. Then I create a new thread. That new thread is going to execute a new transaction. That transaction is from foo account to bar account for $10, transaction 1. And then I start that thread immediately. Another thread is going to be running a transaction that's going to go the opposite way. So from bar account to foo account for $10. I'm going to call it transaction 2. So the only thing we didn't define so far, I think, is the transaction class. So transaction class implements runnable, just like before, a source and a destination account, but this time they are live lock bank account. So I'm using my new class for this code example. There's an amount. The constructor works as with the previous example of transaction class that we saw. So set the source account, set the destination account, set the amount. All of those are passed as parameter and assigned to the corresponding fields. Nothing really new there. We implement runnable, so we have to provide a run method. Here's my run method. While I am not capable to transfer from the source account to the destination account the amount that was specified, then I keep trying. So I have a loop here that tries to make the transfer happen until it is successful. And when it's successful, I just say my transaction completed. And there you go. So now, again, as usual, let's take a look at what happens when we run this, okay? So we start with transaction 1. Transaction 1 is withdrawing $10 from account 1. No problems. Transaction 2 is withdrawing $10 from account 2. Now, because transaction 1 is busy, transaction 2, is busy withdrawing from account 2, when transaction 1 tries to put the $10 it took from account 1 into account 2, it's not able to get the lock. So it refunds account 1. So it took $10 away from account 1 at the first step. Now it's refunding them during the third step. And then what happens? Transaction 2 failed to deposit in account 1 because account 1 was still being held by transaction 1. Right now it's doing a refund. Okay? So it's going to refund account 2. And then we go again. Transaction 1 tries again. So withdraw $10 from account 1. Transaction 2 withdraw 10 from account 2. Transaction 1 fails to deposit in account 2 because transaction 2 is already holding the lock on that account. It starts refunding account 1. Meanwhile, transaction 2 tries to deposit in account 1, but hey, it's being refunded by transaction 1, so it's not available. So transaction 2 tries to refund account 2 as well. And so on and so forth. So this loop here, this block of transaction is going to keep repeating ad eternum. And this is an interesting thing about live locks, is that code executes, the CPU is busy. If we were accessing database, etc., we would generate a load on the database server. So we are extremely busy, pretty much going nowhere. All right. So these illustrate the main problems that we want to discuss in the context of this course regarding concurrent programming.